Good boy, Oswald.
Yay. I got 3 coins. Oh, wow. I'll go give Emma her coin. She likes them. Or to give them away. Oh.
What's your team name again? No, he didn't. He got a team. Yeah. There's also supercalifragilisticexpialidocious. I think that was
Yeah, that was. I think y'all had it. Didn't you have it?
No.
It was definitely somebody from. Hey, hey.
But I was on that team.
Right, are we ready to go? We y'all are still stuck. Working through, working through.
We'll return this pencil.
No, there is. Yep. What have we got? Lamb? Who's lamb?
I thought we were going to do the thing where we together and
No, y'all are all done. That was fast, wasn't it? That went by very
we didn't have time to
quickly.
do part C.
That's okay. Some of you didn't get to it. I'll write about it in the email.
We did.
Good. Good, good, good. Oh, is he good boy? Okay.
Today. My grandma's dog is like 18.
18. Hang on. Need your favorite. Oh, look at this. This dog is not at all spoiled.
Right.
All right, we about ready again? We round up everybody else. Just gotta get going. Look at everybody's getting a stretch on. All right, so we're going with lesson 12. Welcome to Q2. You made it. Yay. There you go. Made it to Q2. Survived. Outstanding. So everybody's test came in by this morning. Everybody's test has been graded as of now. If you sent extra credit electronically, like through an email, I got at least 1, Those will be added this afternoon because I haven't gotten a chance to do that yet. Anybody have any questions about that? Okay, if you haven't already submitted for extra credit, it's too late now, so oh well. Fortunately, there wasn't anybody who failed to do their test because that would really stink because progress reports are going to come out as soon as I get it all averaged together today or tomorrow. Yes, sir. Did I add what?
What was the extra credit points?
So if you want extra credit on a unit test, how do you get it? Use it. You can get the end of any chapter or unit in the book that's corresponding with what we've done. There are questions. There are also questions sometimes within the sections. During a chapter, you see little questions at the bottom. You can submit how many? Can submit 3 for extra credit. All right. The way it works is you can only get up to what is the equivalent of 105%. So say you've got like 75 out of 76 on your test, and I do the associated math necessary. Even if you get all 3 extra credit points right, that would put you at like what would be way over 105%. So I'll cap it there. But if you're, if you didn't get close to the score you wanted, it's always good to hand it in. You have to hand it in before the test closes, which for this test was when? When did this test close? 8 a.m. today. Always that, right? Unless there's some weird exception. That's the rule. Yeah.
Did you add the Tuesday point?
That's on your midterm. Okay, so speaking of Unit 3 test, we're going to go over the most missed questions. And I wrote here, ooh, those are messed up. Well, anyway, we'll come to those in a minute. I wrote here, take note, and I literally mean that. You may want to take some notes according to this, because you may see some of these questions again. And if you didn't get it right, So these shouldn't be visible yet, but they are. So, oh well. How about this first question? All right, the question read, your family drives 20 miles into Atlanta for a concert. You leave home at 4 p.m. It's a realistic scenario. So your dad was whipping along Georgia 400 for the first 10 miles southbound at 75 miles per hour. He soon reached a typical Atlanta backup, and before you know it, you're at a standstill for 15 minutes. Turns out it was a result of another cow truck dumping bovine all over the highway. As you finally pass the scene of the accident, you peer out the window and see a deputy chasing a terrified cow up a hill. You arrive at 6:30. This means your average speed was blank. Okay, this kind of question is about what do you need to know and what is extraneous. 64% of you got it right. If it's going to be less than 70, we're going to review it. Okay, 64% of you got it right. The first thing you need to realize is there's a lot of extra junk in this question. Because word problems, though people tend to dislike them, that's really what math is. Like math is kind of useless without understanding what you're doing. So it kind of has to be a word problem. So in this case, there is a ton of extraneous stuff you don't need. You don't need any of that business. All you need to know is you went 20 miles, you left at 4, you got there at 6:30. What's your average? Okay, so 20 miles took you 2.5 hours. You went 20 miles divided by 2.5 hours, it's 8 miles per hour. In Atlanta traffic, sometimes that's about right. Right? Yeah, you could be hauling along, right? See, you gotta realize you don't need to know that it's your family or that you're going to a concert. Who cares where you're going? Who cares who you're with? Sorry, family. You don't need to know about how long you were going at first. If your question is average, it doesn't matter if you go slow for part of the time and fast for part of the time. Remember your lab when you walked the circuits? The circuits were different, but your average, right? That's what we're looking for. So none of that matters. All the cow business, that doesn't matter. It doesn't matter that it was a cow. It doesn't matter the cow was terrified and the deputy went up a hill or down a hill. None of that matters. Cross it out if it's in your way. Like literally cross it out like this. Okay. So the next one, to describe motion accurately and completely, what's necessary? 57% of you got this one right. What are we looking for here?
I wrote wrongfully.
Is he wrongfully gained? What do you look for here? Frame of reference is what we're looking for. Some of you said, what?
I wrote speed and direction.
Okay.
Not true.
Speed and direction to describe motion accurately. Well, direction you really can't describe without a frame of reference, technically speaking. So it's the frame of reference that we need here. So this one tripped up a lot of people. I think you were looking for something more complicated. This is verbatim from your slideshow, which is verbatim from your binder. Word for word for word for word. And frame of reference was on your review topics. So if you see frame of reference on your review topics and you get to the end of your test and you're like, I don't know if I use frame of reference anywhere. Is there maybe somewhere it could have been? You kind of go back and look and go, oh, you know what? I think that's supposed to be frame of reference. Always a good safe bet to give it a shot. Okay. This one tripped up the other group as well. Change in position equals initial position minus final position. 50% of you got it right, so half you got it wrong. Is this true or false? Everybody's like, okay, sorry, yeah, it's false. Okay, why is it false? Somebody, James.
Because if you subtract the final position from the initial position, you get negative. Initial position.
That's right. Final minus initial, not initial minus final. That's why I even wrote read carefully at the beginning of the sentence. All right, you're learning a new line dance. You take 5 steps to the left, 2 steps to the right. What distance have you traveled? 57% of you missed this one, and this surprised me. If you take,
But I second guessed myself. I was like, well.
if I get in your car, okay, and I drive 5 miles to the gas station and 5 miles home, how many miles have I added to your odometer in the car? 10 miles, because I went 10 miles of distance. So if I take 5 steps to the left and 5 steps to the right, what distance have I, or 5 to the left and 2 to the right, or whatever it said, what distance have I traveled? 7 steps. Yeah, 7.
So distance is the total you travel.
Distance is the total. Think about it just like the car odometer. If I borrow Mom's car and I drive to my favorite girl's house and I hang out and then I drive back from my favorite girl's house, how many miles have I added? That's your distance. How much mileage distance did you put on those tires? How much gas did you suck up? That's the big one, right? Okay, now 57% of you got this one right. You mastered the first line dance, so you move on to a new one. You take 6 to the left, 3 to the right, 2 to the left. Okay, do it in your head. So we're gonna go to the right. 1, 2, 3, 4, 5, 6. To the, and then what was it? 3 to the left. 1, 2, 3, and then 2. Where do we end up? 5 what? To the left. If you lost credit on this, chance is it was because you didn't write to the left. I'm asking displacement to the left. So if it's a, yeah, that'd be fine. 5 left, 5 to the left. If you just wrote 5 steps or 5, it's like, you gave me something that isn't even distance here, right? Because your distance would have been what?
Distance would have been
11 steps. Yeah, very good. All right. 62% of you got this one right. In your own words, describe Newton's second law of motion. Give an example of how this law is observed in everyday life. Okay, this is the hard one to remember. Newton's first law is what?
F equals MA.
No, that's 2. That's this one. What's the first one?
Every action has an equal and opposite.
That's
reaction.
3. We're getting there. What's 1? What's 1? Yes. An object in motion. I write it when I wrote it on your test, like for some of you, I wrote it down to make sure that you had the right answer. I wrote like an object at rest / in motion tends to stay at rest / in motion unless acted upon by an outside force. Okay, that's your number 1. Number 3 was every action has an equal and opposite reaction. Number 2 is the weird one, right? It's F equals ma. Or force is proportional to mass and force is proportional to acceleration. So F equals ma. Here's a good example. Moving a heavy vehicle will require more force than moving a lighter vehicle, okay? In this case, the m is what we're messing with, right? This is the variable we're changing. And if we were to change the F, for example, think about the lab with the cars over here, the checkered flag. You push them the same. You push one harder with more force, right? In that case, you're going to get an increased acceleration because force and acceleration are proportional, force and mass are proportional, right? So when I said, look at your lab that we did, was it 9? What lab was it? 9 or 10? The one with all the 10 Newton's laws. We went all around the house with balloons going everywhere. That one. The whole point is, if you get asked this question again on a midterm, and you might get asked this question again on a midterm or a final, have that example in your head already. So you're not sitting there going, oh, what's a good example of that in real life? Just go back. You have it right there. You already wrote it down. We did it in lab. You've got it, right? So you don't need to even think of it. Just memorize one for each of the 3. All right. If there's a block with a mass of 2 kilograms and a force of 20 newtons is acting on it in the positive x direction, you can substitute left if that helps you. And a force of 30 newtons is acting on it in a negative x direction, you can actually substitute right if you've put left for the other one. Then its acceleration would be what? Okay, 36% you got it right. Okay, to show you where most of you screwed up. Because you're going 20 newtons going this way and 30 newtons going this way. What's our net?
Negative.
Or 10. It's 10. Yeah, 10 going in the negative direction, but it's 10, right? Because we're talking about what's the net force. The direction's the negative direction, but it could be left, right. Like I said, you could substitute east, west, whatever the opposing cardinal or left, right directions. So most of you that got this wrong missed this bit about the net force. You just went ahead and ran with something else. I don't know what. So if you've got 10 newtons, which moved something 2 kilograms, then you're dealing with 10 newtons divided by 2 kilograms, which gave you an acceleration of 5 meters per second in the positive x direction. Okay, so, oh, no, I should say negative x direction. I'll fix that later. Okay, so there's that. That was where our missed ones. Yes, sir.
Negative 5 is the acceleration.
But it was 10, not 5. I mean, 5. Oh, negative 5. If you wrote negative 5, I might have. I'm gonna make myself a note to double check that one, but
I got half the Pop-Tarts, so I mean, I get half the.
nah. I'm writing myself a quick note to check it, Yusuf. I think it should be corrected on yours, but I'm not sure. Really, what it's asking you though is what's the acceleration, and if it's negative 5, that acceleration would imply that it's slowing down, kind of. So it's not really quite the same, but I can definitely give half credit if you at least got the number right. Question over there, Xander?
No, we were just on the.
You're ready to move on?
I found a boundary point in the value I took from the slide.
Oh yeah.
There's no
Okay.
period at the end of the sentence.
Okay. Well, you can always write it down and on a note or whatever and stick it over there in the folder. That's how I'm keeping track of them now. Yes, sir.
How come it's not plugged in yet? The lights are still on.
I assume this is a generator and he's created some sort of battery power. And then that's just when he needs to plug it in. Or this doesn't look like an electrical plug. This could be something else. I don't know.
He's at his.
Work and power. Okay. First things first, we're going to get these 2 words squared away. We're going to get these 2 names and words squared away in your brains.
What president is that?
Here are the players. You're going to find out who he is. This is Jules. See Jules? Aw, it's Jules.
Hey,
Right.
I get it.
Jules. It takes a lot. Why is it so freaking hot in here? I cannot feel this. Hold on. I'm dying. I'm dying. Cool.
It's Jules, because like Jules the
So, yeah, so Jules. Okay. Jules, it takes a lot of hard work for Jules to mine these joules. So joule is the unit for what?
Work.
There it is, right there. So when you hear the word joules and you're wondering what it's a unit for, I want you to consider the rat in the hard hat. He's working. He's working. Yes, sir. Yes, correct. So joules with an O is the last name of the person that we have gotten that unit from. But an actual name for a person is Jules. That's usually a French name, but not always. This is an actual name. So yes, this is not, that was the next thing I was going to say. This isn't spelled the same way because it's spelled like the name Jules. But if you know Jules is mining Jules, and it's hard work. So if he's Jules, and he's doing work, and you remember that Jules works, then you have to think, well, Watson, this is Watson. And what did Watson do to become the most powerful rat in the world. We often say the president of the United States is the most powerful man in the world. You hear that all the time, right? Okay, well,
Whoa.
powerful person. It's a phrase. I didn't say it was true, but you hear it. So this dude has become president of the whatever doll he decided to put there. But anyway, he is powerful. Clearly, he looks like a powerful guy. He's got on a purple suit. Not everybody can pull that off. So power, watts, joules, work. Got it?
It's not vote for him.
No.
Man, anybody who didn't vote for Watson can just leave. You can just get out now. Just get out. All right. So what's work? Work is the product of two things. Emily.
Force and distance.
There we go. Force and distance. Work requires motion. For a force to work on an object, some force must act in what direction? Colin.
Same.
It must be in the same direction that the object moved. If there is no movement, no work is done. So any part of a force that does not act in the direction of the object, I said it, motion, sorry, does no work on an object. Okay, so there's a giant refrigerator here. Okay, and I'm pushing with all my might and it's not moving. Am I doing work on the refrigerator? No, but I do have muscles in my body that are doing work, right? Because muscles are pulling and putting a force against other bones and things like that. So I do have work going on in my body, but I'm not working on the fridge. Now, if Bailey gets up there and helps me, doesn't help me, Bailey starts pushing the opposite direction. We're both pushing on it and it doesn't move. Nobody's doing any work on the fridge. But if she suddenly just like knocks me down and bowls me over, she's done more work than me, right? You wouldn't do that to me, would you? No, we're friends. So yeah, but see, so you have to be working on the object and it has to have a direction. Like I can push on this all I want. I'm not doing work on the desk until it moves. Then it's changed direction in some way. Turned, move forward, pulling force, moving backward towards me, right? You have to be doing some kind of change in direction in order for there to be work being done. Yes, sir.
So according to this, it takes more work to push a pencil than it does to hold 6 bowling balls at a time.
I'm not following your example.
No,
What?
because you can move the bowling ball. Yeah.
To hold them?
Yeah, it's to hold them like still.
Ah, okay, that's a good question. So if you're holding the bowling ball, you're actually creating an opposing force because what is working on the bowling ball?
Gravity.
Gravity. So gravity is doing the work and you're opposing it, correct? So you're not technically doing the work in that case. If you're taking a pencil and you're moving it, you are technically doing the work because you're the one that's moving it. So in science, you do work on an object when you exert force on that object, which causes it to move in what? Chloe? Cause the object to move. You're doing work on it if it's moving what? In the same direction. Okay, so this dude is pushing a cart. Presumably, the cart is moving the same way he is moving because he is pushing it that way.
It would be entertaining if it wasn't.
That's not how it works.
It would be, yeah. And it's clearly work. He says so. It's work. I don't know what he's got on this cart, but it's really cool looking. I was very impressed with whatever that is.
Fancy diffuser.
Something like that, yeah. It's very interesting. I love it when I tell it to make like a steampunk machine. It just creates stuff. And sometimes if you really look, it's those things that don't work, like the gears don't go together. Have you ever seen the meme? It was put up by a school and it said something like education is working together, but it had like creativity on one gear and another gear had like learning and another one had something else. But when you looked at it, there was no way that they could actually function together. Like if one gear turned, it would cause them all to jam up. Like if you just looked at the illustration, it made no sense. It's like a science joke meme because people are like, did you look at that before you put it out? There is no way that could happen. Those gears would all grind up and it wouldn't work. So calculating work. So what's the J, Miss Bailey? There you go. Our joules. Okay. Joules are the SI unit for work. 1 unit of force moving an object 1 meter is called what? We've done this one before. Xander.
Newton meter.
Newton meter. All right. Where are you here? There you are. It's a Newton meter and we abbreviate it NM. Okay, so this makes sense, right? If you think about it, if you move an object 1 meter, the amount of force required is a Newton, right? Because we did that before. We discussed how 1 Newton is the amount of force it takes to move an object 1 meter. Well, joule is that actual Newton meter combined. So we know what a Newton is. A Newton is the amount of force it takes to move an object a meter. And then a Newton meter, that actual act is the work. The force that is moving the object, that is the work. So it makes actual perfect sense when you think about it, when you break down those parts. So just know this, sometimes when you see this awesome triangle, the D is shown as an S. The D in this case being what? Distance, right? So sometimes they show it as an S. Just be aware that you may see it that way and be like, huh? All right, so we're gonna take a second or two and work these. We're doing one at a time. So paper, pencil, again, no hands up. I'll tell you when. So yeah, there's paper. Oh, let me hand it. So you guys can pass around.
Okay, hold it.
Oh, you're good. Yeah, here. Sorry, pass this around. And here, here's something for you guys if you need paper. There you go. You have paper. All right. So your first question is, how much work is done by a force of 50 newtons moving an object through a distance of 10 meters in the direction of the force? Did you have a question about it?
No.
The answer, no hands. Give people a chance. I don't want carrots. I get carrots if people answer too early. Write it down. Oh, you see it on here, the N's not capitalized? It's a font weirdness.
No, it's how much is done by a force 50 newtons. It doesn't have the of.
Oh, you're right.
I like how it has like the W and then like the division symbol.
Uh-huh, that's helpful too.
That's an interesting way to look at that.
Mm-hmm.
I didn't see that.
Yep, sometimes it's like that instead of a little T.
I like the T better though, because then it's well.
I think the T is streamlined, but
Yeah, it's easier to like draw.
yeah,
That one makes more sense. when you
this
look
one,
at
yeah,
it.
really, yeah.
I think I just make a page with all these triangles.
There, if you look at the back of your binder, there should be.
I rearranged so I'm not.
Oh,
using
you have it?
so-
Wait, here, Annalise. Back of it, 'cause
Uh,
most of them are there.
I rearranged
Yeah.
it so it's so much easier than having to carry.
Uh-huh, multiple things.
Yeah.
All right, so Colin, you wanted to volunteer? What'd you get?
500.
500, what? 500 what? What's the unit? How much work is done?
Yeah.
So it's 500 what? Joules. Okay, so how do we get there? All right, we know our force is 50 newtons, our distance is 10 meters. Work is force times distance. So 50 newtons times 10 meters is 500 Newton meters or 500 joules.
So Newton meters are joules.
Yep,
Okay.
you got it. All right. Next one, if 20 joules of work are done when 2 newtons of force are applied to an object, how far did the object move? No hands. We give people a minute.
Would it be the same answer if you wrote NM as joules or? do
You
have
could write it either way,
Okay.
really.
I know sometimes it's very specific, other times it's not.
Yeah. I mean, it depends on the application, but for most of the things we'll do it. You could do it either way, but in this instance, if you write joules, it shows that you know that Newton meters are joules and it's not just Newton meters. Right, does anybody want to volunteer? Okay, all right, Lucas,
10 meters.
10 meters. Okay, so how do we get? We have 2 newtons, 20 joules. There's our distance is work divided by force. 20 joules divided by 2 newtons is 10 meters. There you go. Okay, in the direction of the applied force. Technically, this little bit here should be there. Because it didn't just move 10 meters, it moved 10 meters in the direction that the force moved it. Okay, last one, I'll give you a minute. No hands, give it a minute. If an object moves 5 meters with 35 joules of work, how much force was applied? All right, anybody want to give it a shot? All right, Miss Ridley. 7 what? How much force was applied? What's our force unit? Not joules, not meters, the other one. Yay, okay, all right, newtons. So you have 35 joules that caused 5 meters of movement. Work divided by distance, 35 joules divided by 5 meters is 7 newtons. Good job. All right, who the heck is Joule? All right, he's this dude. Yeah,
That blurry guy.
if it, these are they're a little slow to load today, but, all right,
That name, the Prescott sounds familiar.
a fancy name.
Today's story is about an English mathematician, physicist, and a brewer. A scientist who linked between the heat concept and the mechanical work and hence the formulation of the first law of thermodynamics. By such discovery, his name was named after the energy measurement unit.
His name was named,
In
not
short,
well put.
He is James Prescott Joule. On New Bailey Street in Saltwood, James Joule was born in 1818. He is the son of Benjamin Joule and Alice Prescott, where his father was a rich brewer. Joule was affected by the ideas of the chemist William Henry and some engineers from Manchester when he was young. In 1835, Joule studied at the University of Manchester alongside the English chemist John Dalton. Electromagnetic engines and their strengths and drawbacks in comparison to
I don't know why
steam
that
engines
says
were among
gingins,
Joule's
but
initial
whatever.
scientific concerns.
That's a weird.
His involvement with the family brewery helped him to focus his attention on engines that increased productivity. Joule was focusing on the management of his father's brewery, where later he improved his father's business by replacing the steam engines with a new electric motor that he built. In 1840, Joule published a paper describing the Joule law, stating that the quantity of heat generated per second in a wire carrying a current is proportional to the wire's electrical resistance and the square of the current. As a result of that, the SI unit of work was named after him. In 1843, he did a famous experiment that proved that heat is a type of mechanical energy. In 1845, he delivered his paper on the mechanical equivalent of heat to the British Association in Cambridge. Joule computed the mechanical equivalent of heat as 4.1868 joules per calorie of effort to raise the temperature of 1 gram of water by 1 Kelvin. Joule received honorary degrees from Trinity College Dublin in the year of 1857, the University of Oxford in the year of 1860, and the University of Edinburgh in the year of 1871. In 1878, Joule was awarded a civil list pension of £200 per year for his contributions to science. In the year of 1854, his wife and infant son died. He never married after this traumatic incident. Joule became very ill in his last few years of his life. To keep himself going, he relied on a well-earned salary from the British government. Joule died on October 11, 1889 in Salem and is buried in the Brooklands graveyard with the number 772.55 written on the grave headstone. This number refers to one of his discoveries, which is the climacteric 1878 measurement of the mechanical equivalent of heat. That was a brief biography of the English physicist and mathematician, James Joule. We hope that you enjoyed it. More stories.
He likes
will be
numbers.
coming, so ensure that you're subscribed and click the bell button.
Numbers and probably beer because his family were brewers, right? Interestingly, a lot of brewers, in this case, he is a brewer in like, you guys back there, you good? In this case, the Prescott and Joule families, they had this brewery, but it was a commercial brewery. But a lot of these guys that you find that have done some great scientific discoveries were monks, and there are a lot of monks that were also brewers, if you didn't know that. There are still monks. Actually, there are monks in this state that are brewers. That's what they do.
Because they drink so much.
Drink a lot of beer all day. Well, you know,
Monks
pray,
Well,
Take
maybe
the-
alcohol opens the mind, and that's how
Yeah.
they discover.
pray, take a stein, pray, take a mug. I don't know, but
So much mushrooms.
there's that. So the power is the rate of doing, oh, Milo. There you go. Power is the rate of doing work. All right. And the rate of work. So doing work at a faster rate then is going to require more. Jordan. I was going to say Jordan. Yeah, there you go. More power. There you go. So if you're going to do, if power is the rate of doing work, then you're going to need more power to do faster work. Faster work, not more work, because it's rate, not quantity, right? Okay, so to increase power, you can increase the amount of work done in a given time, or you can do a given amount of work in less time. Okay, so think of like, let's think of a lawnmower, okay? If you wanted a more powerful lawnmower, you would have one that increases the amount of work done in a given time, meaning perhaps maybe it has wider blades and it can cut more in the same amount of time, or it can do the same amount of work, but in less time, which would mean it could cut the same size yard, but faster. Maybe it drives faster. Okay, so these are the two ways. So if we're going to calculate power, it's going to be what? Caitlin.
Work overtime.
Work overtime. Okay, this is when y'all should for sure memorize. And you know it's like right here, right? This is our little tagline. If you never caught it before, it says knowledge equals W divided by T. But what's W divided by T? We just said it.
Work overtime.
But what is it?
Power.
Power. Knowledge is? Miss Annie, you're so creative. Yeah, there you go. Knowledge is power. So I say knowledge. And if you think about it, if you do the work and you put in the time, you get the knowledge, right? And knowledge is power.
College students don't get that.
No, unfortunately, full-grown adults in the business world don't get it either.
And they also seem to don't understand
Yeah.
how money works at a job,
No,
which is crazy.
people expect to get paid because they showed up. That's because they got a trophy when they played a season of soccer, even if they stunk and never left the bench.
Uh-huh.
That's how it goes. Okay. Yeah. So work ethic is important, people. I think that's what we're getting at. All right. So the SI unit for power is, Emily? There you go. There's a watt. Remember Watson? Wonder what he did to become the most powerful rat in the world? Watt. So a watt is equal to 1 watt per second. Oh, Milo. A joule per second. All right. 1 joule per second. So then, now we have some more. So your first question is going to be, how much power is produced by a machine that runs at 50 joules every 100 seconds? So here's where you have to know that joules is the unit for work. So if it says 50 joules, you know that's where the W is in your equation, right? All right. First, let me ask over here. Do either of you want to volunteer an answer? Because I don't have anything from either of you yet. No? Do you want to volunteer it?
Not really.
Not really. Okay, that's fine. All right, I'll go over here. Jordan.
2 watts.
2 watts. All right, let's see what we have here. So our work is 50 joules. Yes,
Is the W on the pocket triangle for watt or word?
work. So I just said watts. 50 work, sorry, joules. Work is 50 joules. I don't know why that ends there. Ignore the end. Because I copied it from the previous page. Okay, and then in 100 seconds. It does 50 joules of work in 100 seconds. So power is P
Okay, yeah.
equals W divided by T. So 50 joules over 100 watts is 100 seconds, sorry, is 0.5 watts, because power is watts and W is work. Yes,
This one's definitely really cute, Brad.
I like him. I like his giant pen.
Yes.
He's prepping it with his arm. So this is the only thing where these get confusing. You have to remember, and this is where it gets funky. You listening back there? So your W is work, and that's joules. But your P is power, and that's watts. That's another W. So sometimes when you see this little triangle, you would put like in parentheses next to the P, it's like watt or a little W, so you remember that it's watt. And then next to the W, you put a little J, so you remember that it's joules, right? And by the T, you can put a second, so you remember that that's the unit. Because basically, these aren't the units here. The W and the P and the T aren't the units. They're the type of force or power you're dealing with, right? So 0.5 watts. All right. How much time will it take a machine that requires 100 joules to produce 200 watts? So joules is that W there. That's work.
It says 20, not 200.
I'm sorry, 20, not 200. I read it wrong. And then 20 watts. So the watts is where your power is, right? All right, Colin, you're dying.
5.
5, he says. Okay, let's see. So you have 100 joules, which is your W, your work, divided by your P, which is your power, 20 watts. And that is going to give you 5 seconds. 5 seconds. All right, now our last one. How much work can be done by a machine that produces 4 watts per minute? Read closely. 4 watts per minute.
The equation you want to use the per time.
Mm.
Something 1 minute or 60 seconds.
What's the unit we use in this equation?
Second.
Seconds. Mm-hmm. That's what you need to do. Hand down. Wait, please. Put it down all the way. Give people a chance. There we go. Okay, does somebody want to take a stab at it, Bailey?
240 joules.
240 joules. So you've got P and T. Your power is 4 watts. Your T is 60 seconds. And you get 240 joules. Nicely done. All right. Our cute little purple rat didn't lead us astray. So horsepower and James Watt. This may be one of my all-time favorite AIs. That's freaking cool, man. That is freaking cool, right?
I want to see someone actually.
I thought it was going to give me crap when I put that in. I thought it'll never get anything neat. And then that popped out first try. I was like, whoa, awesome.
First try too. That's
I know it. So horsepower is, okay, Yusuf, 746 watts. Okay, this is random. 746.
I was gonna say, how do we get
Yeah, we're gonna go with that. That is a really strange thing. 746 is not. Yeah, the only other units we have like that are odd numbers are things like 365 days. You know, that's weird. 60 seconds, 24 hours. Those are weird numbers. They're not metrics. So here's why. In the 1700s, the horse was the most common source of power. So Watt used it as a basis for comparison to describe his power outputs of his what? What do we call this? Okay, Caitlin.
steam engine?
Yes, his steam engines. All right. Who's ever seen a real steam engine anywhere? A train or anything else? Yeah. Super cool. So I highly recommend if you're ever in Detroit for any reason whatsoever, and there aren't a whole lot of good reasons to go to Detroit, but should you be there for any reason, the Henry Ford Museum of Innovation is there, and it's massive, and it's part of the Ford plant where they have the what's it called, River Rouge factory, where they produce the F-150s and all that, which is also a cool tour. But in the Henry Ford Museum, they have the original steam engines that ran the original factory as it rolled out the Model Ts. These steam engines are about as big as the floor of this level of this house. They are freaking massive. And there's not just one, there are multiple of them. They have several that are still preserved, and it wouldn't fit in the area we're sitting in. It would not. It's huge. And there's like ladders around, you can climb up on it. They're massive, huge, huge. But they ran the factory initially. So that's when you think about steam engines, you've got little ones and then you've got big ones. Actually, I have, hey Drew, can you heat up a cup of water for me, please?
Oh, yeah. I bought her that.
Yeah. This is a Stirling engine. He's gonna warm up a cup of water for me and you'll get to see it in action. It's similar. Okay, so we're gonna talk about Watt for a minute while the water heats up. If I could, these are just loading today, like super slow. Here we go.
I like to not be my lips though.
True.
In the heart of 18th century Scotland, against the backdrop of the Industrial Revolution's dawn, there lived a man whose inventive genius would spark a profound transformation in human history. James Watt, born in 1736 in Greenock, Scotland, emerged as one of the most influential engineers and inventors of all time. Watt's early years were marked by an insatiable curiosity for all things mechanical. As a young instrument maker, he displayed an innate talent for craftsmanship, which would soon become a hallmark of his engineering prowess. It was this talent that led him to a chance encounter with a malfunctioning steam engine in 1765, a moment that would forever change the course of his life. Upon examining the engine, Watt recognized its inefficiency and pondered the limitations of contemporary steam engines. His keen analytical mind, combined with an unwavering determination to solve this problem, led him to invent the separate condenser in 1769. This brilliant innovation allowed steam engines to operate with unprecedented efficiency by preventing the loss of energy during each cycle. Watt's groundbreaking invention revolutionized industry, transportation, and manufacturing. His steam engine became the backbone of the Industrial Revolution, driving machinery in factories, powering locomotives, and propelling ships. It was a force that not only transformed the economic landscape, but also reshaped society itself. James Watt's contributions extended far beyond the mechanical realm. His tireless work led to the development of standardized measurements for power, with the unit of power, the watt, bearing his name. This symbol of progress became a fundamental concept in science and engineering, ensuring that Watt's legacy would forever be woven into the fabric of human knowledge. Despite facing numerous obstacles, including financial challenges and setbacks, Watt's dedication to engineering excellence remained unyielding. His engines continued to evolve and improve, embodying his relentless pursuit of perfection. James Watt's story is more than a narrative of invention. It is a testament to the power of human innovation and the boundless potential of the human spirit. His enduring legacy serves as a reminder that one individual's determination and ingenuity can catalyze monumental change, shaping the destiny of nations and leaving an indelible mark on the course of human progress. As we reflect upon the vast transformations brought about by the Industrial Revolution, let us remember James Watt as a visionary whose inventions not only powered machines, but also forged the engine of human progress itself. His life story is a timeless inspiration, underscoring the incredible impact of innovation, engineering brilliance, and the unwavering pursuit of excellence. If you found James
So
Watt's
it
video
said-
inspirational, please consider subscribing.
It
because we
said
have-
that his machines, his steam engines were the backbone. Oh, no, stop. Lord have mercy. Quit doing it. Did it go away? No, it didn't.
In
Okay,
the
good.
heart of 18th
Yeah, we know that.
century Scotland,
Stop.
whose inventive genius,
Goodness.
born in 1730.
Why are you lighting me? Thank you. Set it right there.
Watt's early years.
Okay, we know about what. It just doesn't want to move on. Thank you. There you go. So it said, thank you. So while this, while we wait on this for a minute, it said that Watts.
Doesn't, you have to kickstart it.
I don't know. Did it go on there?
Yeah, it has to heat up.
I know. So it said that Watts, whoa, what's happening?
Looks like a rat. Very.
Anybody want to try it? This is a very similar concept. It's called Stirling engine. Drew, how's it working?
Well, pushes the hot air up. Oh, there we go.
So the hot air is going up because the cooler air is sinking down. Yeah, it can go
Yeah,
real fast.
It
We'll keep
pushes it
going.
up, which pushes this piston up.
Okay, so there's like a diaphragm in here. Okay, so heat isn't really rising, right? Cooler is sinking. That's how it works. Cooler air is more dense. It's sinking beneath. It's pushing the warmer air in this cup up, right? And as it pushes it up, it forces up. I'm going to turn it sideways so you can see it. There's a piston right here. It's a nice hot cup. It pushes that piston up. When it gets to the top, it has a little bit of release and it's jointed on this wheel. It really wants to fight me. You can see how it's jointed there. See, now I'm not even kickstarting it. It's just going to go. But that's a Stirling engine. So it's a very similar concept. You can get these on Amazon. Like Drew said, he bought that for me because it's freaking cool. I mean, do that with your morning coffee or tea. Why not, right? That's awesome. Who doesn't want to drink tea that does that? I want to drink tea that does that. That's fun, right?
One way to cool it down.
And look how fast it goes. I mean, it sucker's moving. So it's a very, very similar concept that we're dealing with. So as I was saying, it said that Watt, his steam engines were the backbone of the Industrial Revolution. So tell me about the Industrial Revolution as far as ecology goes. What was the ecology and the nature and the environmental situation like during the Industrial Bailey?
The moth story.
Oh, the moth story. Okay, what's the moth story about?
So in England, there was a lot of white moths, but then as soon as the Industrial Revolution started, there was so much coal and soot that everything turned black. So then the white moths basically died out because they couldn't hide, but then the black moths were able to hide on the soot-covered walls, so they survived. And then it reversed once the coal burning, the whatever went down.
The population shifted.
Yeah.
So what Bailey just did is what I want all y'all to do. Bailey just connected a lesson from biology 2 years ago to today. That's exactly perfect.
And that's the moth story.
Wait, the moth story is it's very memorable. So that is the moth story is sort of like a staple of natural selection when you're discussing natural selection, and natural selection being the driver for evolution of species. Like evolution is a theory, but you can actually see natural selection occur in real time. Whereas evolution is like millions of years, and people go, did that really happen? The way that it would happen, according to Darwin, is natural selection. And that's a perfect example. So it was one species of moth that was the something or other peppered moth. I can't remember the name exactly, but they were white with black dots or black with white dots. And the white ones could blend in with the birch and poplar bark pretty well. The birds didn't see them as well, didn't pick them off. There were more white than black. Then we get to the question I asked, what happened during the Industrial Revolution? Well, you're talking spewing soot and ash and steam and smoke into the air. Steam's not making a big problem, but all the other stuff is. Everything got coated with black yuck. The trees in the forest were covered with black, and now your little white moths are just like, it's like, hey, come eat me, pretty much. And that's what happened. Suddenly you had more black and less white. And then when they learned to clean things up a bit, it shifted back to its natural state, which was less black and more white. So if a steam engine, which the waste product is heat and steam, why is everything so gross and black and sooty and polluted in the Industrial Revolution? Jordan, you want to try?
They needed to heat the water.
And what were they heating it with?
They were heating it with coal and
Coal and wood. And are these things clean when they burn?
No.
No, they're gross. You know, the guys in the steam engines, like even in the old cartoons, there's a guy shoveling coal into the train. Or if you've ever seen like,
What do you think of Polar Express?
yeah, I was gonna say Polar Express or Titanic, where they show you Polar Express, you can see them doing it on the train, and then it's in Titanic when they run through the engine room at one point. Jack and Rose are sweaty, and they're running through the engine room. What are you gonna die? And they get, you know, they come running. There's all these men down there shoveling coal to keep the big pistons moving on there. But I love the memes that show the area that Jack's body could have covered had they moved and different.
No.
I'm gonna put this here so you can watch it. All right, so question. Okay.
I remember this one time my friend got
Wait a minute. Lucas is saying something. Go ahead.
my friend found a moth like this big,
Oh.
and it was just on him. It was just chilling. Like some of us just came up and pet it, and it just sat there.
Was it green?
I don't remember that.
The biggest ones around here that you are most likely to see are Luna moths. and they don't live very long, which is very sad, but they are stunning. They're green and they're about that big. So power in machines. Now let's talk power in machines. Okay, machine is a device that changes what? Changes something. What does it change? Either of you? Still don't have, well, I got one from Drew because Drew volunteered about the Stirling engine. Okay, Yusuf. Not power. Changes, what? Jordan?
Force.
Change the force. Yes. Okay. Machine changes a force. That lever you use today is a simple machine. We're going to go very, very slowly through simple machines. Don't worry, that's coming. And that is going to be important because your Rube Goldberg project is going to be composed entirely of simple machines that make a giant compound machine, right? Uh-huh.
Am I allowed to just make my new golden machine out of Legos?
There will be some, there's some allowance for things like that as part of the structure, for sure. It's outside, it's going to be big. I also, just so you guys know, years and years ago, I inherited an insane volume of Connects. Connects are, they actually will function with Legos because they will interlock the way they're built, but they're like tracks and they're little cars that get launched. And so I actually started yesterday, I pulled the box out and it's just been like, it was a jumble. It was given to me by a friend when his boys aged out of it. And it's a giant bin. And I started going through and sorting it all so that it's neat and organized yesterday. And there's way more of it than I thought. And I will allow you to check out those to use as part of your Rube Goldberg. I'll also have some Legos you can check out, things like that. Check out, meaning you have to give them back to me without damaging them. So machines can make work easier to do. They can change the size of a force, the direction of a force, or the distance over which a force acts. Look at all these guys with all their little machines working away.
I don't like how tall that one is.
Yeah, this one's a little awkward. Maybe these are the students and he's like the professor.
Math.
Sometimes they do that though. Sometimes like I'll ask for a rat and it'll give me literally like a rat's head and person hands or
It's
Cool.
the rats from the nutcracker, it's fine.
yeah.
Whoa.
So increasing and decreasing force. He's a big sucker. So a small force exerted over a large distance becomes what kind of force? Small force over a large distance becomes a Xander. Becomes a large force. Yes. Okay. And then a large force, a small force exerted over a large distance becomes a large force exerted over what kind of distance? Use it. Yeah, a shorter, smaller distance. Exactly. Okay. So you have a little small force, you exert it over a large distance, it becomes a larger force exerted over a short distance. And if you have a large force exerted over a short distance, then it becomes a, Lucas, small force exerted over what kind of distance? Xander? Yeah, a longer distance. Okay, large distance. So these are, how do we term this proportionality? What's the term we use when they're opposite, when the proportions are, one goes up, the other goes down?
I just remember that.
James? Inversely, yeah, inversely proportional versus directly proportional. Okay, so this there, you see their car broke down. He's trying to push it. I don't know, he pushed it to the mechanic. There's a mechanic. All right, so increasing and okay, let me just tell you, this one was one of the hardest ones because half the machines it created for me made no sense, and this one doesn't make a whole ton of sense, but don't look at it too hard. Okay, so don't look at it too hard. It's a jack of some kind. I assume.
The rat is now as big as the car.
Right. My assumption is that you have to turn this through for this to shift up or down to move the truck.
What happened to the back wheel?
The car got smaller.
That car is meant to ride like this. I don't know. Okay, so increasing and decreasing of distance. So a decrease in distance over a force, over which a force is applied, does what to the amount of force required? If you increase the distance, how does it change how much force you have to apply? You want to guess, PJ?
No.
No? Jordan, you want to go?
you need less force over a larger distance.
Right, there you go. So when you increase the distance, okay, you decrease the distance over which you're applying the force, you're increasing the amount of force required. Think back to your lever from just a little bit ago. Okay, where is one? There's one sitting right here. All right. Thank you. All right. I'm not going to beat any of you today. Maybe next week. So if you put this little guy, I'm going to have to sit him right here so you can see it. All right. I think he's good. So if you are decreasing the distance over which your force is applied, this is an increased distance. This is where's the force being applied? The effort is from here to here, right? All right, so it increases the amount of force required to lift, whatever is going to be on that end down there. The opposite way, it's a lot moving around down here. Yes.
The squeaking from that is really annoying.
Oh, I thought I was.
It
Relax.
sounds like a clock.
It's very relaxing.
No, there's like
No,
a
it's-
breach noise.
No, yeah.
There's a really
Wait a
high
minute,
pitched
really?
noise.
Yes.
That's probably one of those things young ears can hear.
I thought I was the only one hearing that.
That's fascinating.
I can't hear it.
Tell me if it goes away or comes back. That's
It's on.
Done.
y'all have, okay, that's another thing. So that has to do with sound wave frequency. So whatever you were hearing was at a high hertz level, it was a higher frequency sound. And the older your ears get, the worse you are at hearing high frequency. If you want to do something really fascinating, get a good pair of headphones or earbuds. Okay, don't do it in like an open room. Go on YouTube and search it, but there is we'll probably do it actually as a group in the room, which isn't as good as headphones, when we get to hertz. But it will take a pitch and it starts it at a very, very low hertz level and it increases the frequency. There is suddenly a point where, the screen's just got a number moving on it. And there's going to be a point where suddenly you hear it. And then there's going to be a point where you don't hear it anymore. And those two endpoints are different for every person. So
Mine
it's
was off and on, like I was
kind of
not
cool.
hearing.
Yeah,
And then later on, I'm doing it. It's like, wait a minute.
it's fascinating.
I really thought.
I'm glad y'all said that because all I heard was tick tock, tick tock, tick tock, tick tock. Interesting.
I didn't hear it.
My head now is really annoying. It's like you're bouncing.
Fascinating. So if a decrease in difference increases the amount of force you need, then obviously an increase in distance is going to decrease the amount of force you need. This is again your inversely proportional thing. All right, so let's talk about some levers.
Oh.
This is a winning AI image. How cute is this? So we've got chopsticks here as an example of input work, output work. All right, a large input force and a small input distance. Your input distance here is very small. Your thumb is pretty forceful. You're using a good force here. And your output distance is greater. So your output force is small. Here's your large output distance. You're definitely using more force here than occurs down here. Who can use chopsticks? Who can do it? Oh, I had to give y'all a homework assignment to learn how to do it. If you have trouble learning, you can take them and you can roll like a little piece of paper in between the top two and then wrap a rubber band that keeps them slightly separated, and then you can kind of start to learn to use them. Some of these images were the creepiest images of all time. I tried to get a rat's paw holding the chopstick so I could make this, and I gave up after about 20 really creepy attempts. So I was like, it would be like this, it looked like something from Halloween. It was like this like freaky hand with claws, and it was real gross. Or it was like a person with like rat nails. Yeah, it was gross. All right, now here's an example of a small input force, a large input distance. So a wheel and axle is a great example. So it only takes a small amount of force to turn the little wheel, but it goes much farther because it's a screw, basically, which we'll be talking about later. So your output force, you like him, huh? So your output force is large and your output distance is small. I liked the tub. I tried to get a tub with a faucet. Apparently that was not, I was asking too much, but still, you get the point. He had to fill it up somehow, right? I don't think he carried buckets. Got little bubbles on his head. Yeah, there you go. It's behind his head. It's one of those side ones on the side. Hey,
The buckets of on the
Very
other
cool.
side.
It looks so much cuter when there is no faucet. Like you see the little water in there.
why not? All right, so here's another example of where you've got a machine
Like that's
changing
working out.
direction. So we had machine increasing distance, machine increasing force, machine changing direction. So when he pulls down on this lever at the gym,
No way
because
he can at all.
he is attempting to get swole. So when he pushes down, the weights are gonna go.
Have you tried getting a muscly rat? from the
Just
vet?
you wait. Just you wait.
Guys, send us an email how it looks after the gym.
Oh, it's coming. He's cute. He's working hard.
Yeah,
Here, stop.
rat.
So when you pull, this goes up, obviously a very, very clear example of a machine that changes direction is a pulley. It's like the first one you think of when you talk about a machine changing direction, a pulley. So work input and output, dun, 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 because what? I know,
That's the USSR.
I know it's a little weird, but he's not necessarily a nice rat. The work done by a machine is always less than the work done by a machine, sorry, it's always less than the work done on the machine because of what? Because of friction. Okay, friction. See this nice smoky, steamy stuff? Some of that's probably from whatever he just blew up. But would you put your hands on that barrel? Why not? It's nice and hot, isn't it? Ooh,
Drills,
stop. Yeah.
drills are a very good example of that.
Oh.
Screwdrivers.
Drill. Okay, Bailey's got to get guys back there.
Bring the hard way.
Yeah. Did you touch something that a drill? Yeah.
While we were making our room, we had a screw, not like screw, like drill,
Yeah.
a hole
Mhm.
so that the plywood
Yeah.
crack. And I accidentally brushed against it, not thinking anything of it.
Oh yeah.
And I got a good 2nd-degree burn from it.
Yep.
Ooh.
That'll do it.
Yeah. I and it was only 2 holes that we had drilled.
I have
So it heated up very quickly.
downstairs
from
under the deck. I have I wanted something to store the yard tools in, so I actually found like on Facebook Marketplace somebody's getting rid of an old gun cabinet, rifle cabinet, which was perfect because it's like tall. And I thought, okay, well, all I need to do is drill holes like with a hole drill, like a
Oh,
the kind that makes a circle, and I can pop them in. And while I was drilling those, there was legitimate smoke, like burning. The wood was burning just from the heat of friction. That's like when anybody ever successfully started the fire with the stick and the thread and the rock? You ever done it? I've done it. It takes a lot of work. Anybody at the back table? Y'all with me? Y'all ever done it where you take a stick and you make like a little bow out of it, just tie thread, and you rub it back and forth real quick and you try and get the stick to start a fire? It's a thing. You can do it. You can for real do it. All right, so wait a minute here. If energy cannot be created or destroyed, only changed, then what happened to the energy lost due to friction? Caitlin?
Turns into heat.
It turns into heat, as Bailey was just saying, you burn yourself. So in general, a lot of energy is converted to heat that you don't think about as much, but that's really, it happens constantly all around you. This is why if all of us are in this room today and I'm like, oh my gosh, it's so hot in here, it's because all of y'all are putting off heat, and that heat is a byproduct of the aerobic respiration going on in your cells. And that heat is the byproduct of that chemical reaction. So the same conservation of energy is going to apply to a chemical reaction as applies to a physical reaction or any sort of force moving, anything like that. So it doesn't get lost. It just becomes heat. Yes.
He's standing on a single line. Do you think anyone can ask him to do
You know, I hope nobody runs him over because he's real cute.
He also has extra toes.
Oh, he does.
That's an A.
He, does anybody know what that's actually called if you have extra digits?
Oh yeah, he's missing.
There's a word.
He's missing.
He's,
I know
you only
the
have
word, I
3
don't know what.
fingers holding
Well, you can't really see all his fingers, but there's definitely an extra digit. You know what it's called?
Inigo Montoya's enemy.
Inigo Montoya's enemy, Milo. Does anybody back there know what it's called when you have extra digits on your fingers or toes? Polydactyly. Anybody know anybody with polydactyly? I do. You know somebody? Your dad's friend? Does he still have, guys, back there, side chatter. Does he still have all his fingers? Does he have an extra one? Just one? Does it have bones? Do you know? So my cousin's son was born with an extra little finger on each hand, but there was no bone in it. It's just like a little finger with a little nail. So they actually like tied them off, just tied them so that the circulation went away and they just eventually fell off. But she called him his monster fingers for his first couple weeks of life because he was little.
I would always think like if you were born with it on your foot, I would hope your parents would have. Otherwise, shoes would be very uncomfortable.
Some people that are polydactylic have it's fully formed, it's a bone, it's everything, it's just extra. But if it's not a bone and it's not connected, very often they'll remove it. And in my cousin's kid's case, it was an easy peasy thing because they just tied string on it and it just died. You know,
If you have a red outfit.
because he wants you to see him. Stop. Says stop. All right. So work input to a machine. All right. The first force exerted on a machine is what, PJ? Input force. And then the distance through which the input force acts, Emily? Input distance. And then the work done, the work done by the input force through the input distance is Ridley. There you go. All right, y'all got this. Very good.
Wait, the rat is actually hovering over the seat.
He cannot reach the pedals. I believe this is like a maidenhead on a ship. I'd like to think it's a stuffed animal. You know how people sometimes hang the Buzz Lightyear off the back of their car? I'm thinking
No,
that's
because the rat on the bike, he's floating above the seat.
He's not touching it.
no, it's a white seat. He's on it. All right, so work output of a machine. So the force exerted by a machine is okay, Lucas, output force. And let's see, if you haven't answered a question yet, remember that you're gonna have to if you want your binder points. What now? Would you ask? Oh, he could be. He could be an Oppenheimer rat. I didn't ask specifically. All right, what's the distance through which the output force is exerted? Emily again. Output distance. And then the output force multiplied by the output distance is James. Force times distance. Output, work. It's work. Force, distance, work. And in this case, we're talking about output. So it's work output.
Brownie point.
Yeah.
It doesn't say distance. It just says it says the output force multiplied by the output. It doesn't have this.
Oh, I think it's cut off by an image. Yeah, I think you had an image run over. By the way, before we totally leave that binder, if you look in your binder, there's a little thing on the side column. I think it was like kind of tan in color, and it talked about horsepower. That explains why the number is so weird. Yeah, it has to do with how much power the average horse actually put out. That's for real how he came up with the weird number from actual horses. Yeah, no. So you think about a car, that's a lot of horses, like actual horses. That's a lot. Yeah. So in summary, your input versus your output. Work is done by forces on objects. Your input force is the force made by you on the machine, and the output force is the force made by the machine on the object. Input work goes into the machine, output work comes out of the machine. The work of a simple machine can never exceed, the work output can never exceed the work input. Why? Friction. Your answer is friction. Your work output can never exceed your input because you're going to, quote unquote, lose some energy in the form of heat from friction. So you're not really losing it, it's just converted. And now it's in the atmosphere or whatever. It's not your perfectly closed system. Yes.
If you had given that rat like long hair and a hat, it would have looked like Professor McGonagall.
Kinda. He's cool. All right, so we got this nice industrial factory and we got this dude here. This is fun. So there he is. This was me trying desperately to make something work, and eventually I kind of gave up on it. So that was all you get is him doing that, because it was just like Oh, there we go. I spent too many hours and then I was just like, it's not doing what I want him to do. I give up. I was trying to show like changing direction by using this as a pulley, the shorter distance and the greater for, and then I just was like, I give up. He's just gonna do this and that's all he's gonna do because I can't, but he's cute. I like his machine. All right, so you will get your progress report sometime in the next 48 hours. I want to have them done tonight. I hope I have them done tonight. So you will need to be sure that you look for them. It will come as a separate email, as a PDF, okay? And your tests should be accurate. Yusuf, I'm gonna check that one thing you mentioned, but everything else should be accurate and good to go. Can everybody now see Q2? If you look at your grade book, you can see it.
Yeah.
Should be open. You should be able to see Q2.
Oh, yeah.
What will happen is Q1 will disappear sometime within the next week. It will be hidden from you. Your grade is saved, like what you made for Q1 is still saved. And all of your individual tests and your individual labs and everything you've been graded on individually, none of that's gone. It just is going to disappear from your field of view because it gets to be way too much. So how your grade works in the long term, it's not as if I take your first quarter grade and your second quarter grade and come up with a semester grade as an average. I don't do that. I do all of your tests, labs, your midterm, all those things get averaged as one big unit for your semester. At the end of your second semester, I'm not taking your first and your second semester and averaging them. Again, I'm taking every individual assignment from the whole year. So just because they're gone doesn't mean they're gone. They're not gone, really. You just can no longer see them. I'm going to find, well, just for the heck of it, if anybody's interested, I'm going to find that the video with the Hertz that I was telling you about. So if you want to go, you can go ahead and go. But if you want to stay and watch that, you can. Just you have to be very quiet because you have to listen very closely.
Wait, like the little pictures for the lessons after today, you already have them like done?
You mean the slides?
Yeah.
Some of them, not for every lesson. Are you looking for something in particular or?
Well, I was just thinking like for one of them you could like do like a Wizard of Oz theme and and then the giant like
The Great and Powerful?
Yeah, but
That could be fun. I never thought of Wizard of Oz theme.
The hologram thing that he does, it could be
Oh.
Ozzy as the Wizard of Ozzy.
Oh, that's interesting thought.
From there.
Wizard of Ozzy.
And teacher, can you change my like
Mm-hmm.
I'm in 9th grade now, so
Oh,
and it
it
still
didn't
says
change
I'm
it.
in-
Yeah, you're in 9th. You're in 9th and it says something wrong. Okay, I'll fix that. Okay, so this is the Hertz range video. I'm gonna actually turn the volume up a little before I start it. If you want to listen, the way to do it is this. You raise your hand.
Once upon a farm, we took the new.
You raise your hand when you hear the sound, and you put your hand down when you no longer hear it. Here, can you scooch guys? Okay.
Money.
All right, so your hand should be down, and then when you hear the sound, you just shh, you raise the hand. When you don't hear it, you put your hand down. Ah, some of you heard it all the way to the end, right? It's pretty cool.
That I think you're struck with at a really high rate.
Yeah, it's interesting.
It's kind of hard to hear during the beginning and
1
end.
hour
Because it gets kind of.
Yep. Yep. And there's, oh, there was just one that said, how old are you?
I didn't hear from the beginning, but I heard it all
That's
the way
true,
to the
too.
end. Yeah, I heard it all the way.
Too
the
old
end,
to
but
hear
I just
that.
thought I was
This was
for a
me
second.
today. Too old to hear that. Yep. So these are the ones that old people can't hear. So why my hand went down before y'all. Not a medical test.
Okay.
I have to give that disclaimer.
Oh, yeah.
Can I do something?
And watch the circle, the number. That's your guesstimated age. Based on averages.
I feel like my ears like stop.
See. Mm-mm. Yeah. You're 30. That's crazy. He's dead silent. Wow.
Okay, it says I'm a that I am.
And mine cut out at 42 and I'm 47, so that's pretty close. Right?
Mike is like 15, I'm 11.
There you go. That's pretty good. If it cut out at 15 and you're 11, that's pretty good.
It cut off at that's 16, but I just turned 15.
Yeah.
Right.
Okay.
I have three.